So here it is, what you've been waiting for the entire semester, right? The fundamental theorem of calculus. Emphasis on the fun. Okay, sorry, that was lame. Anyway, this theorem, all right, this is what all of calculus has been building up to. I told you first day we were going to take limits and we were going to link limits to the derivative, and then we were going to have integrals, and we were going to somehow link the derivatives to the limits and then the derivatives to the integrals. So everything is all intertwined together. So here it is, the fundamental theorem of calculus. This is the fundamental theorem part 1, right? Yeah, this is kind of like those videos where it's like, Rocky 1, it was so good. And then Rocky 2, it's like, oh my gosh. And then Rocky 3, oy. Just gets worse as the parts get more and more, right? Okay, and y'all are like, what the heck is Rocky, right? Okay, so theorem 5.4.1, the fundamental theorem of calculus. Let f be continuous on the closed interval a to b, and let capital F of x, which is the antiderivative, be defined as the integral from a to x of f of t dt. This t in here, we call that a dummy variable, not because it's dumb, just because it's a dummy. All right, so then I'm all full of jokes today, right? Golly. All right, so then f is a differentiable function on a to b. The open interval, we're differentiable, we're continuous on the closed. Guys, that's like a common thing going through calculus, right? We want it to be continuous on the closed, differentiable on the open, okay? Then if that is the case, if I take the derivative of the antiderivative, then I will get the original function, which is intuitively what you kind of already knew, all right? But now we're literally putting it into the fundamental theorem of calculus. So let's show you in a picture over here. So I've got this picture over here, and I've got my function. This function is f of t. So this is on an interval t here. So x is just some arbitrary t value. So where t is equal to some arbitrary x. That's all we're saying, okay? So the function is continuous from a to b, all right? And x is some value between a and b, maybe b itself. All right, so we start at a and we go to x. So we're finding the area under the curve. So my limits of integration will go from a to x. We start at a and we stop at x. So that gets the area under the curve here. That's what I'm talking about. Now, I define my function. You know, typically a function would be like x squared plus 2, right? So that would be a function. But this function is not defined in terms of some polynomial. It's defined in terms of a integral, which is kind of interesting. First time you've seen a function that's not defined as some polynomial. So everywhere I see an x, I plug in an x, right? So the only place I can plug in something for this function is that upper bound of the limit of integration. Okay, kind of cool. So what this does is this function, the bigger x gets, the more and more area that is accumulating starting from a up to the x value, okay? So like if a was like equal to, I don't know, 1, and b was equal to like 5, you know, this x here, maybe if that x was like 3, okay, then I would plug a 3 in here and I would do a 3 here. So I'd integrate from 1 to 3, okay? If the x instead was like a 4, the only thing that would change, this would still be a 1, but I would put a 4 there. A 4 would go in there if that was the case. But we're keeping it arbitrary, so we're just going to call it x. And so I plug an x in here, I get the x in there, okay? So what this function represents, it turns a definite integral, so a definite integral from a to x, okay? Remember, definite integrals produce area. It turns it into a function now, a function of x, where the larger x gets, the bigger your area becomes, right? So like if I had like an x value here, a smaller x value here gets me a smaller area. Like if that's x equal to 2 versus, here would give me like an x equal to 3, which would give me a larger area, right? And so as x changes, the area changes. So as I make x bigger and bigger, the area gets bigger. So the area is changing. So it's letting the upper limit x be what's variable. The function where the variable changes, it varies here. Okay? This is really interesting because now the question becomes, how does that function antiderivative of f change with respect to x when I take the derivative, right? So this is an antiderivative, okay? It's the area under the curve from a to x, So it's everything under the curve from a to x. Pretty cool. So what does this mean? What does this mean? All right, pretty crazy stuff. I want to know, how is that area under the curve changing whenever I change that next intermediate x value, right? So whenever I change the x value, how is the area changing? Well, to find this, I take the derivative of this function here. And when I take the derivative of that function, it equals, well, what is that function equal to? That function is equal to the integral from a to x of f of t dt, right? And so I take the derivative of the integral of the integrand here, and what do I get? I literally get the integrand, but instead of evaluating it at t, I evaluate it at x, which is that variable right there. That upper limit tells me what to put in here. Pretty amazing stuff going on right there, okay? So pretty amazing how it turns such a complicated problem into something uber easy. So let me give you an example, okay? So right now I have the antiderivative defined to be equal to the integral from a to x is the variable, of t cubed plus e to the x dx. Now, I want to find the derivative of the antiderivative. So what am I going to do? I'm going to take the derivative of this, and so that means I need to take the derivative of this. So this is equal to, remember, the derivative from the fundamental theorem of calculus says the derivative of the antiderivative is just the integrand evaluated at x. So I'll literally take my function here, and everywhere I see a t, that's my dummy variable, right? Everywhere I see a t, I'm going to plug in that variable x. So instead of t cubed, it's going to be x cubed, and instead of e to the t, it's e to the x. And that's my answer. How easy is that, right? Students have a hard time with this problem. This is supposed to be the easiest problem in calculus, okay? If I'm taking the derivative with respect to x, and I have an x in the upper bound, I literally replace my dummy variable with the x variable. And that's it. I mean, it doesn't matter how complicated this is. If I'm taking the derivative with respect to x, integral from some number 1 to x of, 5 to the y minus sine of y cubed dy, where y is now my dummy variable. Everywhere I see a y, I'm going to replace it with x since I'm taking the derivative. So that becomes 5 to the x minus sine of x cubed, and that's it. You just took a problem that there is no way that you could integrate this. You just don't have the tools to do that right now, okay? No way for you to integrate, particularly being able to integrate this piece right here. You could integrate this one. I guess that would just be 5 to the y ln, or divide by ln 5, right? But this one here, you don't have the tools to do that one right now. So pretty cool that we took a problem that was really complicated and we just wrote out the answer like it was nothing, okay? So fundamental theorem of calculus part 1, very, very powerful. So now what I want to do is I want to consider inspiration for part 2. So consider f defined on some open interval containing a, b, and c. So I've got a b, and a c, so a, b, c. And so I've got some function here. All right, so pretend those are vertical, right? So what do I know? The integral from a to c is everything, okay? So that integral of f is everything, but this is equal to what? We can split this integral up into 2 pieces from a to b, integral from a to b of f, and then here from b to c, so plus the integral from b to c of f. As long as you stop and start in the same spot, then you're going to start and finish in the same spot as your original, okay? So that's that idea. We've talked about it before, but I wanted to go back over that, make sure we understood. So then what do I say? The integral from a to b of f of t dt, remember the t is your dummy variable. This is equal to what we just said. We can break it up into 2, where we go from a to c, and then we start back at c, and what do we want to finish with? We want to finish with b, okay? And so now what I'm going to do is I'm going to use another property, okay? So instead of having a start with a and end with c, I'm going to start with c and end with a, but if I switch the bounds out, if I flip the bounds here, what happens? Well, I get the negative out front. Remember that property from properties of definite integrals? And then I'm going to keep this the same. No reason to mess up something that's perfect, right? Okay. So now what am I doing here? What am I doing? I'm going to use the definition that I had here. Okay. Integral. So the antiderivative f of x equals the integral from a to x of f of t dt, right? Okay, so what is this? This is the integral from a number to a to x. So I'm going to plug in an a into my function right there, right? And so whatever's in that upper limit there, that's what goes in here, right? That's why I switched the bounds. And then whatever went in here, that's what went in there from our definition, right? So what does that tell me? That tells me that this is defined as this right here, and then I just carry the negative down, okay? What about this next one here? This is equal to plus capital F of, well, what is the upper limit? B. So I plug in capital F of B here, okay, by definition of what we found up here through our definition. If we define that to be the antiderivative. So capital F is the antiderivative of the lowercase f, the integrand function. So what does that tell me? That tells me that see right here, I just explained that, okay? So this is the fundamental theorem of calculus. It says that the antiderivative is equal to the integral from a number to x of f of t dt, right? So everywhere I see this upper limit, that goes into here, just like this. B went into there, and that A went into there, okay? I picked up the negative here to here. So if I reverse this around, I flip that around, I'm going to get f of b minus f of a. So what have I done here? I have now linked together the definite integral, so we can evaluate a definite integral using antiderivatives. So what am I saying here? The integral, the definite integral from a to b of f of t dt is equal to the antiderivative evaluated at b, the upper limit, minus the antiderivative evaluated at a, the lower limit. Very powerful here. So this shows how the indefinite integral, the antiderivative, and the definite integral are related to each other. Okay? And this, my friends, is the second part of the fundamental theorem of calculus, which says that if f is continuous on AB and capital F is the antiderivative, any antiderivative, that means like if your antiderivative, say you had like a derivative of 2x, that's like my favorite one, right? Then the antiderivative, if I integrate 2x, that's x squared plus c, right? So when I say any antiderivative, I mean like it could be x squared plus 3, x squared minus pi, whatever, right? When I take the derivative of this antiderivative, I get 2x. That's the idea, okay? So I'll literally take any antiderivative, and then if I evaluate the antiderivative at the upper endpoint, and then subtract it from the antiderivative evaluated at the lower endpoint of the interval we're integrating over, then I get the exact value of the definite integral. Pretty amazing. It links the definite integral to the indefinite integral evaluated at the upper and lower limits of integration. Very powerful stuff. In the next video, I'm going to prove this theorem for you.